actually measures size using something that we call a Ferret diameter. Basically, it's a diameter measurement, but it's done at angular intervals. So we actually do 4 different measurements. So we have like a 0, your 180, and then your 2 in the middle, your 45, and your 135. So you're actually getting almost like a full cross-sectional size measurement. So that really helps with particles that aren't round. If it's spherical, then obviously your diameters in all directions are going to be the same. But if you have like a long or thin particle, or an irregular shaped particle like this, then actually we are looking at that entire shape of that particle. So the average of our particle size then becomes the average of the particle size is measured, then is reported as the average of the 4 Ferrets. Because we are a camera-based system, we're taking images of every single particle. We can trace other useful parameters that we need for morphological analysis. So things like perimeter, so we're tracing the edge of the particle, working out perimeter. Obviously, there's pixels based with the camera, so we can actually count how many pixels that particle is covering. And based on a pixel count, we can do things like area. And then based on size and area, we can now work out particle volumes as well. So for looking at particle size, like I say, average of the Ferret, that gives you your particle size. When it comes to concentration, because we are working out the volume of the particles that we've analyzed, we also then know at any given time the volume of the fluid that has passed through the analyzer. So your concentration in ppm is a volume of particles over volume of fluid analyzers concentration. So you are actually getting distinct separate numbers. So you're going to get, it's like a 4-in-1 analyzer effectively. You are going to get your oil ppm as one value, your solids ppm as one value. And then on top of that, you're also going to get a full oil droplet size, excuse me, distribution, and a full solids particle size distribution. And then in terms of looking at some morphological algorithms, these 2 really simple ones, but it's how we look at shape. The basic one that we always tend to use is shape factor, and that is basically a ratio. It's the relationship between 4 pi area and the perimeter. And effectively that gives you a ratio between 0 and 1. A perfect sphere would have a shape factor of 1. And what we effectively say for the software is we say things like, well, so oil droplets are going to be round, so it's as close to a perfect sphere as we're going to get. So oil droplets are going to have high shape factors, and solid particles are going to have low shape factors. So we will actually show you this running when we go out to the workshop, but this is a still screenshot of what our ViPA software would look like if it was running. You always get your live video screen on the top left here. You can change all the graphs. The user has the ability to plot whatever graphs they ultimately like, depending on what they are most interested in. But typically, if you're looking at produced water, what we tend to plot is oil and solids concentration. So that's what this graph is. So it's a continuous plot because this would be running typically online 24/7. So it's versus time. So plots will just keep going. But that's concentration. So your red dots here is oil concentration, and your green dots here are solids concentration. And then the second graph at the bottom here is the mean size in microns. So again, it's against versus time. So it's a continuous plot, but your lighter green solid dots, your lighter green dots here, oil mean size, and the darker green dots here are solids mean size. Just below your little live video table, you tend to get the actual published value. So this is plotting the graphs, but if you wanted to see exactly what that number was, you could look here. So like I said, you're seeing your oil concentration, your solid concentration, your oil mean size, and your solid mean size. So the full distribution is given. It's done in the background. It's just hard to show all of the numbers on screen at any one time. And the interval at which you update the data when you're running continuously is also a user inputable thing. So typically it tends to be every minute. So basically every minute it analyzes a whole series of images, counts all the particles that it sees, works out the size distribution, works out the concentration. So at the end of every new minute, you will then get 2 plots on this graph, 2 plots on this graph. So 4 new numbers would populate here. And obviously the software can also run rolling averages in the background. So this is looking at the current cycle value, and then the number next to it is giving you your rolling average over again, a user set period of time. And in this scenario, it's a 60-minute average. So you can see here, for example, that you get sudden highs, but averaging over a period of time, it's actually lower. In some instances, that's the sort of thing that customers need to know about when they're running their systems, as to whether you're just going to get a one-off high value, or whether it's actually an alarm condition that you want to raise. So in terms of connecting online, really, it's very, very simple. We run a sort of bypass system, so we don't actually necessarily go inline. So it's online as opposed to inline is how we refer to it as. In a perfect world, we would like to connect to a sample point that has vertical upflow on your process site. So that just basically gives the most representative sample data. All your solids are running through that vertical section of pipe. If at all possible, especially for fixed installations, we would recommend a sample quill. So there is a quill that then goes into the center point of that pipe. So any particle, any fluids that come through the ViPA is basically, the most representative. And then really, we don't need much else. We just need the ViPA connected to it. You'd get isolation valves, I guess, for the sample point. And then ultimately, you'd want to connect that to a drain point, or it can be returned somewhere else in your process, provided it's a slightly lower pressure than your sample point. Just going to show you a few pictures. So like I said, we did several different models of ViPA. The technology is the same for all of them, really, in terms of the core technology for the camera and the lighting and the software. And the differences are really whether it's hazardous area rated, mobile, fixed, or not. So this particular one is our smallest, most compact. It's called the ViPA B. It's designed to be like your benchtop sort of analyzer. So it's more for non-hazardous area use, indoor, so either in a lab or in a safe area. We can easily connect sample points, just like if you have a bottle sample, you can gravity feed it through the analyzer, like this image is showing you on the left. Or this is actually another image showing the ViPA running online. So there's some flexible hoses connected to the sample point, going into and out of the ViPA. And the ViPA B typically, because it's meant to be small, it is connected to a laptop, but any control computer, it can be a desktop if you so choose as well. Then we have fixed skids. So these are our permanent installations. So they tend to get connected on site, right next to or as close to your sample point as possible. And these are hazardous area rated zone 1. Our analyzer enclosure typically looks much the same for all our systems. So the electronics inside it, as I was saying, is the same. To get hazardous area ratings for zone 1, we need to have a PERD system. So in this image here, we basically got your analyzer here, a PERD system that basically connects instrument air into the ViPA. So for a couple of minutes at the start, it needs to basically run a purge through the enclosure, make sure there's no explosive gases present inside, and then basically we're safe to run. So for systems like this, where the ViPA is on site next to or as close to the sample point as possible, what we actually then use is fiber optic cable. So this is a little fiber junction box. So the ViPA sends the images from the camera to this little junction box, and then there'll be a fiber cable that goes from here to the control computer, which is typically in the safe area, usually in the control room. And then from the control room, that computer can output all the data and all the alarms that ViPA produces to the local control system, SCADA system, anything that the customer wants to basically have logged. We also have our more bespoke systems, where basically we will design it to suit customer specifications. So this is one of those. So this, for example, is a fully automated ViPA in a cabinet that's gone to the Middle East. So it's got some cooling and stuff installed inside the cabinet to keep everything at nice ambient temperatures. And then I go on to our mobile units. So these are, again, much the same. That ViPA side technology is exactly the same, but these are designed to be mobile systems. They are hazardous area rated, ATEX zone 1 or zone 2, depending on which model we're looking at. We started off with what we call the MZ2. It was basically a box that had the ViPA, the computer, a keyboard, a monitor, the purge, everything all in one big box. The only downside to that was the box was a little bit heavy because of all the different components into it. So when you're on site and we had to move it around, that became a little bit cumbersome. So then we designed the MZ3. And the idea behind the MZ3 is that each individual component is modular. So it basically makes, I mean, it's still heavy in total, but it makes each individual part fairly light when you take it apart. So the computer is one component, the purge system is one component, the ViPA is another component, and then you can sit on a trolley. So when you go to site, especially if you're offshore, for example, and you need to move the MZ from sample point to sample point, you can just disconnect it and then move each individual part and then reconnect it again. So that was the idea, to make it modular, so everything fits between under the manual handling limitations that we were allowed to have. So it was easy enough to use. So what we're actually going to show you outside in the workshop is an MZ3, because that's the unit we have at the moment here. But what we did actually do after that MZ3 is we designed another unit. So this is our more current unit, and we call this the MZ4. So it kind of went back to the original MZ2 style, except what we did here is we made it even more compact. So we got the weights really, and the sizes as well, right down to as low as we possibly could. So this is back to an all-in-one system. So you've got your monitor, the computer's on the inside of the enclosure, there's a keyboard, you can't quite see, but the top there is the top of where the ViPA flow cell is. So in this image, we're actually using it on site. So you can see the ViPA's running. So that's where the fluid comes in. So there's a sample inlet, a sample outlet. And again, because it's hazardous area rated, we need an instrument air to purge it. So that is a airline connection. So I'm just going to stop there for a few minutes. We're going to go out to the workshop and show you the live demo, and then we will come back to this in a second. Just bear with me.
Thank you, Gayatri. So while we wait for Gayatri, we're dropping something in the chat box. It's like a small quick survey in the chat box. We'll be dropping that there. So, and the whole idea is we want to see how we could actually help you solve your produced water challenges. Just a quick survey, under 2-3 minutes that you can fill while we wait for Gayatri to. So the survey, the link to the survey has been dropped. Gayatri is back.
Hi, so can everybody see an MZ running at the moment?
Yeah, we can see just maybe in my Zoom more.
Excellent. Okay, so I'm just going to move out a little bit so you can see the whole system. So it looks much like the picture I think I showed, hopefully. So we've got a computer unit, so that's the monitor, that's the keyboard. On the other side, there's a purge system. So this is currently connected to our compressor. So sorry if it's a little loud in here at the moment. And then we've got a ViPA unit sat at the bottom there. And all we're doing at the moment is we've got a sample that we're running through using the pump. But obviously, you know, on site in real life, you'd connect that to a live sample point with an inlet and an outlet. But that is it. That is basically what the MZ3 looks like. We apologize that we don't have the MZ4. We were going to have the MZ4 to show you today, but literally just yesterday we had to pack it up, ship it. We have a customer waiting for us to have basically data collected online in Brazil, so we had to ship that out. So it went a few days earlier than I was hoping. So I'm sure we'll do more demos next time, so we can, you know, do another one maybe in the new year. Maybe then we can show you the MZ4. So if you guys follow Jorin Limited on LinkedIn, we'll have more posts, and then hopefully you can find when we're doing our next webinar. And if you're interested in seeing the MZ4 live in action, you can join us then. But for now, I'll just zoom in to the computer screen. So hopefully you can see lots of particles whizzing past on our ViPA screen there. So as I was saying, that is your live video feed effectively. Then to the right, you are getting the graphs that are going to be populated. So every minute a new data point is going to be added. So you can see we've been running this for a little while. Concentrations, we've got oil concentrations in red, solid concentrations in green. And at the bottom here, you've got particle sizes. Again, oil and solid particle size, that's the mean size of the report. And you can see the table that's being populated. And right at the bottom is what we call a live data table. So again, that just continuously populates with every single particle it's seen. So that's a bit fast for you to actually see, because that's constantly constantly whizzing past. But yeah, so that is then what ViPA looks like when it's running.
Yeah, thank you, Gail. So I think we have questions in the Q&A already. Maybe.
Okay. So I'm gonna stop this screen and I'll go back and sit on the desk so I can actually hear everyone.
Okay.
Okay.
So while we wait for Gail to get back to our desk, like we said, we dropped a link, to a survey we're trying to do to see how we can help you better to manage your produced water challenges.
Hello.
Yeah, we can hear you now.
Excellent. Okay, so I'll go back to sharing my screen. But yeah, so you said there were some questions. Did you want me to do that now or at the end, or any preferences?
I mean, it depends. Maybe we can take the two questions now, then you can go back to your,
Sure. Okay, so let me just look at the questions. So the first question, I don't know whether everybody can see it, so I'll just read it out. How does your system camera handle emulsions, surge of slug flow? So effectively, we have a max concentration range in terms of what the ViPA can see, because it is basically a microscope. It's a visual-based system. We're shining light from one end, and the camera needs to be able to pick it up on the other end. So we do have a max concentration, especially for crude oil, where if the solution starts getting too dark, then we won't be able to transmit light across it. So we tend to cap, or we say our max concentration or our concentration range is 0 to 2,500 ppm for crude oil and water. So if there's any surges or slugs or flow in that range, then it doesn't matter at all to the ViPA. The ViPA can still see, we will still report higher concentrations, larger particles. I mean, the screen will obviously go a bit darker, for example, but in terms of ViPA analyzing it, there is no actual concern or issue. We will be able to monitor and analyze increases and decreases in concentration, and same for particle sizes, again, provided it is within that range of 0 to 2,500 ppm. And as there is a concentration working range, there is also a size working range. So we quote our size range as 1.2 to 150 microns. We can actually see smaller particles than that, and we can actually see bigger particles than that, but it's all about then statistically what you can capture with one camera and one optics unit. So that's range that we would say is what works, so 1.2 to 150. So, you know, like I say, if emulsions come through, slug flows come through, provided it's within those ranges, then there's no real issue. We tend to find emulsions, for example, is a bit harder, because then you tend to get a lot of small, very small particles, and emulsions get a bit too, I guess, cloudy or milky in terms of the appearance. So with an emulsion, then you tend to actually probably almost blind the analyzer. So it does need to be a homogeneous mixture of the oil and water at that stage. So, you know, we wouldn't recommend it for emulsions, but obviously if you did get a slug of emulsion, you wouldn't get the most representative data at that point, but as soon as the emulsion's cleared, you'd go back to analyzing again. So the emulsion wouldn't affect, as in, like, you know, wouldn't deter the ViPA from continuing running once the emulsion's passed or once there was a surge of slug flow. We do have cleaning systems for our online units. So like I say, we've got operators, oil and gas companies all over the world that use our analyzers for permanent online monitoring, whether it's for discharge monitoring or produced water reinjection or seawater injection. So seawater, not so much cleaning is required really, but for produced water, we do have a cleaning system. Our cleaning system is basically it's a jet wash. So it's a high pressure wash. Our flow cells have what we call basically a wash port. So they are machined into the flow cell, so they run tangentially to the fluid flow. And the way that the machining is done into the flow cell, it basically creates a high pressure nozzle. So it's a little bit like when you're cleaning the windscreen of your car, where you've got nozzles directed at your windows. So there's no wiper, but there are nozzles directed, exactly machined perfectly, so that when the fluid goes through the flow cell, it hits the windows, each window, and you get a really good mechanical clean of our flow cells. The ViPA software itself is actually constantly monitoring the amount of light that we're transmitting. So we have fouling alarms. So we actually have the ability to say, you know, this is actually in good conditions, it's nice and clean. If fouling has occurred, we'll pause analysis, run a wash, and then check the light situation again, and then continue analysis if it's all okay. Some systems we put in a preventative wash, so it'll just do a wash every so many hours, irrelevant of whether it's fouled or not. It's just like a preventative, making sure nothing is building up. But yeah, so like I say, if there was a slug flow and if it did create fouling, there'd be no issue. We would be able to resolve that with the automated cleaning. So there's another question here. Does your system have the ability to trend quality of produced water and recommend treatment types? So that's a two-part answer. Yes, so the whole point of using online systems like ViPA especially is the trending. So of course you're going to get oil concentrations, solid concentrations, and the droplet sizes and particle sizes all the time, you know, as often as every 5-10 seconds if you want, but, you know, like I say, at least every minute. And that's a lot of data. No one's actually looking at those numbers every minute to see what's going on. So the whole point really is to get that trend. So as I mentioned, I don't know if we've heard, but the bit where we did the graph when I talked about the fact that we can do rolling averages, for example. So that really helps with providing that trend, actually, because you can say actually over the last hour, over the last 2 hours, what are we doing? Is it going up? Is it going down? And then some of the systems we have on site, they look at alarm conditions for, say, produced water reinjection, for example, you know, based on a rolling average over an hour. So you're not necessarily immediately reacting to just a one-off blip. So yeah, we definitely do have great trending for produced water. And yeah, you can use it for treatment. You can use it for produced water management, be it chemical use. There is a slide I'll go to after this. But yeah, when we talk about what all the applications are, and a lot of our customers actually do use it for produced water management. So based on the data is whether you choose to add more chemical, add less chemical, control the actual other parameters of your process. So, like we can change interface levels and separators, differential pressure ratios across hydrocyclones, whether there's other pressure or temperature changes that you want to make just based on the data. And like I say, probably a better answer will come when we go through the applications and some of the case studies. But yeah, definitely you can use it to recommend treatment. I have more questions. Sorry, so it's not too long. I'll continue answering the questions that are coming up. So the next question is, how often does a system need calibration? And the answer is none. It's effectively a camera. So if you bought a camera, you take it out of the box, you're immediately ready to start taking pictures. And it's the same with a microscope. You might need to move it around a little bit to get the focus that you want if you're using a brand new microscope. But we do all the calibration at factory. So we are setting up the camera and the optics to work in perfect harmony with each other and with our lighting. So once we have set that and closed it and sent it out, you never need to change that ever again. So it is factory set at build, never needs recalibration. And that is one of the better things about our systems, is that you don't need to do a 0 ppm or 100 ppm type calibration. You can run it forever without needing to recalibrate. Of course, we have software that's mated to our hardware. So the software does need validation. So we do have some validation steps you'd have to do for new sample points, but it's definitely not a calibration. So I have another question. How is the performance with light or heavy oil? And it's, for us, there is absolutely no differences with what the type of oil is. Whether it's light, heavy, we can do condensate, diesel, kerosene, jet fuel, lubricants. Any type of hydrocarbon in water will produce a droplet. And because we are a visual system, that is all we're looking for. We are just looking for droplets or dispersed particles, suspended material in that. So there is no issue with any kinds of oil in water, provided they form droplets. Because we are visual based, so the only limitation for us is we can't do dissolved oils. So there are some customers out there that want, like, say, total oil and grease, for example. If you're looking at wanting to analyze dissolved oils with a microscope type system, you can't. So we are looking solely at dispersed oils only. And I think the last question is much the same. Are there any limitations in terms of different quality oil, higher or lower API? So again, no, for us, there is no differences in how the equipment runs, whether it's high API or low API, provided the particles, so the oil forms droplets in water, then we can analyze it without any issue. I think I've caught up with all the questions. So again, if nobody feels or they want clarification, just continue asking me questions. I will go back to the presentation now then and continue there. So effectively, what we're saying is it's a water analyzer. So it's a visual process analyzer, but because we are transmitting light and we have a camera-based system, we need the bulk of the well fluids to have already been separated. So in terms of where we can work, ViPA can be used anywhere downstream the first stage separator onwards. So once the gas is removed, once the most of the crude has been separated, and you're looking at just produced water. So it's a water leg monitor only. So this is what we have classified as a typical produced water treatment process. I mean, there's so many different varieties of equipment and separation equipment that companies can use. There's lots of different chemicals that companies can use, but this is just a very typical one. So you've got your well fluids coming in, your first and second stage separators. So your bulk of your gas is removed, the bulk of the oil is removed, and we're now looking at all the water side of it. So this little symbol here is our P&ID symbol for the ViPA. So we're kind of effectively saying we can go from downstream, the first stage separator, anywhere else in that process. So we can look at separator performance, we can look at hydrocyclone performances, we can look at what your further polishing vessels could be, degassers, flotation units, filters, any of those sort of pieces of equipment. And ultimately, if you just want monitoring for if it's going overboard or for produced water reinjection. So for us, a lot of our applications are produced water reinjection because the ViPA gives you that combination of data that we need. It's not just oil concentration, which is what a lot of the analyzers do. Ours will give you oil concentration, solids concentration, and the particle sizes of both as well. So it's a 4-in-1, and that's exactly all the information you need for produced water reinjection. So that really is our biggest market, but lots of customers are using it. We sort of started out more just downstream overboard, so it's a bit like almost like a firefighting measurement where we're trying to measure before it gets too late. And slowly over the years, customers have, I guess, understood more the benefits of the online data. And as I mentioned in one of my answers, it is used a lot more for trending and produced water management. So the further upstream you put it, the more time you have to react to any slugs that are coming through. For example, you can decide on recycle. So there's a slug that's come through, if ViPA is saying your oil concentrations are going up, that water, instead of going through the hydrocyclones and through the degasser all the way through back to either reinjection or overboard, can be recycled to the second stage separator, for example. So that early warning gives you the time to react. We've got a fair few customers that also use it for chemical management. So it helps you if you're doing if you've got lots of wells connected and you have water, especially your water cuts are changing depending on well configurations that you're running, or just the properties of separability on its own are changing from well to well, based on the sizes that ViPA are reporting and the concentrations that ViPA are reporting. They can increase or decrease demulsifier or de-oiler dosage based on that. So actually, in the long term, you can actually reduce the amount of chemical that's being injected into your system based on just reacting to what the data is actually telling you. And if you're monitoring it at that stage and making the changes that you need to the process at that stage, then the chances are you will never have out of spec water for your overboards and reinjections. Or if you did, it'd be very, very short amounts of time before you made all the changes that you need. And I touched on for a few seconds, but the other application is also seawater. So there's no oil to measure here, but seawater injection, there's still solids. Most seawater injection applications have filters, coarse filters, or just filters in general. So, and that also still needs to be analyzed. So ViPA will do the exact same thing for seawater applications, but just report for solids concentrations and solid particle sizes. So I'll go through a few case studies. And again, this isn't meant to be complex information. It's not hard data. It's really just data we've collected over the period of times. We've done a fair bit of consultancy work for many clients. And this is just some really simple examples of where and how using the ViPA to get that online data is really helpful. So this is a hydrocyclone example. So a customer was having issues with a hydrocyclone that recently installed. Basically, it wasn't really doing too much. They were kind of worried they'd spent all this money buying a hydrocyclone and it wasn't actually performing how they expected. So we sent 2 MZs. We connected them to run simultaneously across the hydrocyclone. So the blue dots here is the oil concentration upstream of the hydrocyclone. The green squares here are the oil concentration downstream of the hydrocyclone. So what we did was, for a few hours, we just did baseline, just collected the data as it was to see what was happening. And as you can see here, basically what was coming into the hydrocyclone was what was going out. Not a lot was actually being separated. We just worked out in this red line what the actual removal efficiency was for that point. So efficiency wise, I think the highest we reached at baseline conditions was about 30%. So with that online analyzers running, we said, let's do some really simple changes. We changed things like the differential pressure ratios across the hydrocyclone. So we tried a few different ratios. So like I said, 2 hours of baseline data. We did about another 2.5 hours so of changing some conditions. But yeah, so we tried 4 different differential pressure ratios in the 2 hours and found one that was best suited for those process conditions based on their flow rates, their pressures, their particle size. So going from, their initial baseline average efficiencies of 15–20%, we actually found a condition that could give them close to 80%. So we're now getting closer to operating at what they expect from their hydrocyclone. And like I say, it wasn't at all difficult trying to get the particle size data to be able to do that, and the online information, the concentrations would take a long time to do that in the lab. But with online analyzer, that was all resolved in less than half a day, in 4 or 5 hours. A hydrocyclone that works. This is a chemical one, so this is looking at a deoiler. This one wasn't actually anything particularly fancy. Again, we were doing some trials to prove that the deoiler was going to be suitable, that the deoiler could actually work effectively. So we did some data with the deoiler on, nice compact, lowest concentrations, about 30 to 40 ppm. And oil sizes are a bit more erratic, but that is what the deoiler is supposed to be doing. It is trying to basically coalesce the oil droplets, so it is doing some degree of coalescing here. Then we turned the deoiler off just to see what would happen, and it slowly started creeping up. The concentrations, you can see it's almost more than double the original concentrations. So clear indication that the deoiler was actually working. And then we switched the deoiler back on, and you slowly sort of see the concentrations come back down. And similarly with the particle sizes, without the deoiler, all the oil droplets were much, much smaller. And with the deoiler, you got bigger, larger droplets, and that's the whole purpose, so that the hydrocyclone then had bigger oil droplets that it could separate further downstream. So this is another case study where we looked at just solids for a produced water reinjection application. This is ViPA data downstream their desander. So this particular site had a bit more solids than they would have liked, especially for reinjection. So they put a desander. Now people put desanders, depending on what your solids issues are, different places. They tend to be, in a perfect world, much further upstream, so the bulk of your sand's removed. But these guys had fines more than large solid sand particles. So they had a desander at the back end of their process to remove the rest of the fines that they couldn't remove further upstream. So their reinjection concentration specification was actually about 5 ppm solids. So we're monitoring just to see if the desander is working and they're meeting their spec. So in this first graph here, more often than not, at 5 ppm, we are below that limit. So what actually happens is they do need to backflush their desander, and I believe they do it once a shift, so that's about twice a day. So the only obviously issue is that, yeah, the backflushing is going to help the desander continue to operate to how it needs to operate. But during that backflush, there is an upset. So there's about an hour or so where concentrations increase, and then it takes, like I say, it takes up to the hour just to come back down to where it needs to be again, below 5 ppm. And down here, the exact same sample point, but on a different day. Again, more often than not, we're below 5 ppm, but here they started changing some well configurations, and they actually brought in a higher water cut well. And now their solids concentration started creeping up. So effectively, it's looking at, without the ViPA data, if you had just took some few sample points, you would have thought that you were within the spec for your reinjection, but actually, once or twice a day for about an hour or so, you're going to be out of spec when the backflush is happening. And without monitoring what your actual routine maintenance for well configurations and stuff are, it's very hard to know whether you're going to be within spec. So for this site, what we ended up having to recommend was putting a divert valve in effectively. So before they do a backflush, they divert it so the produced water actually goes back to the second stage separator, and they're not actually injecting all this out of spec water for 2 or so hours every day. So this is a very similar example to the previous case study, but this is more a maintenance thing again. So it's doing sand jetting. So this particular site had a lot of sand that kept accumulating in their first aid separator. So what they were doing is they've got these units connected to the nozzles at the bottom of their first aid separator to basically fluidize their sand. And then they have like these vacuum suction pumps to take out as much of it as they can. So they were actually doing this once or twice a day, but it's a very short, literally they were putting the high pressure water in through the nozzles for like maybe maximum 30 seconds with the idea to fluidize all the sand, and then their vacuum pumps will remove as much of it as possible. So they are actually discharging their oil and their produced water. So they have a discharge spec, roughly about 30 ppm is what they want to achieve. So this is showing oil concentrations at their discharge end, and more often than not, they are below their limit, 20 odd ppm, but sand jetting operations started, and they did 2 quick pulses for sand jetting for this particular example. And obviously the whole point of sand jetting is to fluidize all the sand that's settling at the bottom. So you're going to expect the increase in solids concentration, which is this graph here. So this solids concentration is what they're expecting to happen because we're fluidizing all the sand. But what actually happens that they weren't expecting, but what does actually happen, which is very typical of a sand jetting operation, is that it affects the interface in the oil in the separator as well. So you tend to actually now affect separability where that interface level is, and you're drawing out more oil than you would have just because of the fluidization and the churning up in that separator. So during that process, and that took an hour and a half at least to come back to settle down, but every time they did a sand jetting process, they were actually now discharging up to, I mean, this is the highs of 100, but they are overboarding up to 100 ppm, you know, or at least more than 30 ppm for over an hour, which wasn't something they were aware of. They did take lab samples right after they started one of their, in this example, one of the sand jetting operations, and they did know that they were a little bit above 30 ppm, but it was just a one-off, so they weren't so concerned. But like I say, it's, if doing spot samples, that was what they caught, but they didn't actually then catch the next cycle where it went even higher. So this is another example of where, you know, online monitoring is really going to show you what's actually happening in the process and gives you the time and the ability to make the changes that you need to make sure you're not going to overboard or inject out of spec solutions. This is another chemical one. This one here, we're actually looking at, it's basically a chemical trial. So the customer needed to pick a new water clarifier. They had, it's very complicated, the graph, but in very simplistic terms, there were 3 different chemicals they wanted to try and a varying different number of dose rates that they wanted to try. So chemical trials, typically what you'd get is you do bottle tests. You just get chemists that go offshore, they'll dose different chemicals, they'll do different dose rates, shake the bottles up, see what the separability is, and that is a tried and tested way. It's a great way, something that, you know, everybody still needs to do, but it's a fairly long process. So typically you take about 1 to 2 weeks to be able to qualify a chemical when you're on site. So what we did is we just helped the process along a bit. So we connected analyzers upstream and downstream of their flotation unit, which is where they were going to inject the clarifier, just upstream of that unit. And we just basically helped. So we just looked at a little matrix of the 3 chemicals and what the dose rates they wanted to try were. And we just picked different chemicals, different dose rates. And in about 24 hours, we actually tried all of that and found what the best chemical and the best dose rate was. And then we could hone in and reduce the number of bottle tests to check all the compatibility. So that was a much, much speedier way of doing chemical trials. So another case study here. So this is looking at seawater. So we were looking at a seawater intake, an offshore and an onshore facility. So they're basically taking in seawater and they wanted to spec some filters for how to separate all the silt out of that seawater. And we were just helping with what the solids loading was going to be so we could help with the filter efficiency specifications. And what happens is, because it's actually onshore, very, very close to the beach, you can actually see the effects of the tides in this data. So this is, as you can see, over some number of days. And you can see this very cyclical pattern where it goes up and down, goes up and down. And that's actually the effects of, as the tide comes in and tide comes out, the amount of silt that gets churned up that comes through the intake goes up and down based on those movements of the tide. So again, it's a matter of looking at how high the loadings go based on when all of those movements are happening. And for 3 or 4 days, there were much higher concentrations here. So this was actually it was a summer. This is somewhere in the UK. So we're looking at a date in August. So it's nice summer weather on the beach. There were people out at the weekend with, jet skis and little boats, and they were churning up the actual beach, and more silt was coming through. So these were much, much higher. So the filters that they were speccing was nowhere near that level of loading, because I guess it just wasn't something they were expecting to see. So again, just highlights once again the benefit of the online monitoring is that you can actually see all of those differences. If you just took a few samples every once in a while, you'd never actually be able to see the effects of the process and how it changes over time, and all the external forces that can give you the changes as well to the data. So I think that's where I stop talking. I will look at more questions.
Yeah, Gayatri. There are questions in the chat box, not in the Q&A. I think you've answered I don't know whether you have covered all the Q&A, but in the chat box, there are about 5 questions.
Okay, let me look at that. Okay, so one of the questions I can see here, somebody's asked is, can one device be connected to multiple sample points? And yes, the answer is yes. We do have customers that have that. So they have one analyzer and a basically like a manifold of sample inlets. Some are manually operated, so you send an operator out to stop one sample inlet and turn another sample inlet on, or some are actually fully automated, so they all have solenoids on them and a PLC control, so you can do it either on a time basis where you can say, literally cycle through these sample points and analyze them, an hour each, or you can change it into manual and pick and choose which one you're analyzing at any given time. So yeah, you can be connected to multiple sample points, but obviously each sample point is only analyzed once at a time, effectively with one analyzer. So if you did need to analyze, say, downstream separator, downstream cyclone, and your overboard all at the same time, then you would need 3 ViPAs. So I've got another question here. It's, how did you achieve uniform calibration for all grades of crude, considering oils do have different API? So I don't know whether I covered that well enough, but when we talked about how the ViPA works, effectively, for us, it doesn't matter what the oil is. It doesn't matter what the density of the oil is. All oil droplets in water form round droplets effectively. And what the ViPA is doing is we are just looking for round droplets. So so the density of that, the appearance or color of that makes no difference to how our black and white cameras and our microscopes actually see oil droplets. So in terms of our calibration, all we're actually doing is calibrating the camera and the optics to the lighting and the flow cell. So what we're running through it in terms of whether it's solids or different types of oil, there is no difference, because basically we can analyze anything that we can see. And I think I mentioned quickly, like I say, it doesn't matter that it's not just crude oil that we can analyze. We have lots of different customers that use us for diesel, jet fuels, hydraulic oils, lubricants, any hydrocarbon in water. And in some applications, we have customers that use us in reverse scenarios. So water in light oils, for example, so not crude, because I said the crude would be too dark, so we wouldn't be able to transmit light through crude. But if you've got a say 100% diesel, or 99 something percent, high concentration of diesel, and you wanted to look at water in diesel or water in kerosene or water in condensate, we could do that as well. It's exactly the same principle, because water will form round droplets in that hydrocarbon. So we are just effectively looking at the dispersed round particles in that fluid. Got another question that says, does it come with sample probes? So for the ViPA Bs and the MZs, which is the mobile units, we tend to say no, because it's not a permanent system. You are effectively just going to connect it to a sample point for short periods of time, because the mobile systems are just designed for that. They are for troubleshooting, process optimization, equipment trials, chemical trials. So they are short use, short term. So they tend to just connect to any pressure tapping on your process that you already have. But for fixed systems, yes, we always recommend a sample quill of some sort is installed, and we can provide them, or customers can provide them, whatever is preferred by the end client. So I have another question. Regular maintenance. What regular maintenance needs to be carried out? So maintenance is actually very, very limited for our systems. If you had the fully automated online system, for example, where there's a wash system for it, then basically, maintenance is like biannually, where it's just changing seals and valves and things like that. But in terms of actual ViPA maintenance, if you have a ViPA B or an MZ, then you keeping the flow cell clean is the main maintenance that you want to do. We have like what we call flexible cleaning sticks to clean the flow cells for the manual units. So you would need to isolate the flow, open that fitting, clean the flow cell, and then you can start the analysis again. But for the fully fixed systems, you wouldn't have to do any of that, because our jet wash would sort all the cleaning out for you. So like I said, when it comes to the fixed systems, maintenance is very, very limited. It is just the sort of biannual things, just to make sure there's no leaks, changing seals in valves and those sort of things. So I've got another question, so I'm just scrolling through all that. What happens if turbidity of water is too high? So that goes back a little bit to the concentrations that I was saying. We have a concentration range that we can work to. So we tend to say it's 0 to 2,500 ppm. That's our range for oil and water. But turbidity obviously isn't necessarily always a function of oil. It can be a function, it's predominantly a function of solids. Tends to be fine solids in produced water that gives you high turbidity. So we can actually work with fairly high turbidity water. So provided the particles are still within the smallest size range. So if you're now going into, like nanomicron nanoparticles, then we can't really analyze those anymore. But if you're looking at still, if it's half a micron and above, then high turbidity waters still isn't too much of an issue. But if we're talking very, very turbid to the point where your water is now like, almost like a milky solution, then you wouldn't be able to use ViPA for solutions that look like that. So I have another question about limitations that need to be considered for either temperature or corrosive fluids or turbulent fluids. And so, everything has limitations, but ours are all what we think fairly non-limiting limitations, if that makes sense. Temperature-wise, I mentioned at the start of the presentation, I think we are rated to 120 degrees Celsius. So as far as I know, we have not encountered any produced water application that's gone higher than that. So we're rated for cover all of that really for 120 degrees C. Corrosive, erosive fluids, again, we are looking at analyzing sand. So there obviously are erosive particles in there already. Because the flow cell is made of duplex steel and industrial sapphire, it's designed to be robust. It's very, very hard to detrimentally affect the duplex and the industrial sapphire, because that's exactly how it's designed. So not in terms of erosion. And corrosivity wise, we're actually rated. So as long as we're not higher than pH 13, we can analyze almost any sample. And the only reason for too high, once it gets too high a pH, there are O-rings on the inside of the flow cell that can perish. So it's not that we can't do it, it's just that you'd then have to change the seals of your flow cell far more regularly than we would have ever recommended. So yeah, in terms of corrosion, like so, we tend to say nothing higher than pH 13. And in terms of like actual laminar flow, turbulent flow, none of that is actually an issue. We've got very, very high rated, well, I say it's high rated flows that we can go through the analyzer now with our high flow systems. And because it's effectively just a bypass line, we're going to take a slipstream from that main sample line, so we can actually work with any sample, any actual sample flows, any sample pressures, as long as it's like and temperatures, as long as it's 120 bar, 120 degrees C, there's no real issues with flow rates. I think I may have answered all the questions.
From Charles Wagu on the Q&A. Does the jet wash come with fixed systems?
Yeah, so again, obviously the customer has the option to buy the actual wash unit or not. So we do them as we call them FZ, that would be the fixed ones, or we can do FZAW, so that's the ones that have the auto wash. And the auto wash is effectively a jet wash. So there's a pump, and we connect. Typically, we recommend potable water. So if you have potable water on site, you'd connect potable water to the pump. Whenever the ViPA software either produces a fouling alarm, so when we're saying actually, the flow cell is dirty, please clean me now, it pauses ViPA analysis. The pump will come on, potable water valve effectively would then open, and then you'd get this high pressure introduction of water into the flow cell. The flow cell has, as I mentioned earlier, very specially designed nozzles and ports for the flow through it, into it. It runs perpendicular to the sample flow. So basically it gets introduced into the flow cell at high pressures, and how the nozzles are designed is that it jets directly onto the windows. So there's a very good mechanical agitation that's achieved when that pump turns on. So it's the mechanical cleaning basically is how we clean our windows. So, and that can be based on a fouling alarm. So actually you get a pause, you get the alarm signal, so it pauses, it does a clean, or it can be preventative. So you can set that to come on, every so many hours, just to make sure you don't actually get to a stage where a fouling alarm occurs. So then we've got another question about turbidity. How does it handle high TDS? Okay, so yeah, in terms of TDS, it doesn't, like I say, because it's dissolved, we're not going to see it. So high TDS actually doesn't affect ViPA at all. The only issue can be, like I say, if the water or the solution itself gets too cloudy, and that usually we have found in our experience isn't really a function of the actual TDS. The cloudiness tends to come from either introduction of chemicals, so there's a slight chemical incompatibility there, so it's creating not necessarily an emulsion, but like a hazy appearance in the fluid. But yeah, no, so TDS, we've never actually found any issues for high TDS in terms of it being too high a turbidity for us to work in. Have I got any other questions? Have I missed any questions? Did anyone else have any other questions for me?
I think that's about it.
Excellent.
All right, so I think that's it. We sent out a survey form. So anybody with further questions can just fill that out and we'll pass it across, or we'll try and answer and reply every question on the survey form.
Yeah, if there are any other questions I haven't answered, yeah, definitely do let me know.
All right. So thank you so much, Jorin, Gayatri, for this presentation.
No worries.
And thank you for the answers, and you took our time to answer every question. So thank you so much. Thank you for the audience for this engagement. We'll look further to working with you guys. Please kindly fill the form again so that we can help you out with your produced water management challenges. Thank you so much, Gaia, and thank you everyone. Have a lovely day.
Thank you.